Hopefully you have completed watching the video and taking notes over the percent by mass in a formula. And now we will proceed to look at this empirical formula and then in molecular formulas. So we'll start off with empirical. And so the first thing that you may see when we ask you to do something about empirical and how it's spelled here is you need to look at the formula. So this first slide in your little notes, you can write down a formula. For example, there's a few on here, but I'll give you this one to start off with. You're going to have a formula given to you. For example, C6H12O6. And what you need to be able to see in a formula, if given a formula, when you see the word empirical, empirical means its simplest whole number ratio, its simplest form. Now this molecule here has a larger molar mass because it has all of these atoms to make up that molecule. But to make things easier, we can simply write this formula in a simplified manner. So if I ask you to get the empirical formula, and I give you a formula like C6H12O6, you need to look at the formula and say, can I reduce it? Can I simplify it? Can I divide everything by a number to get simpler numbers? And then that's my empirical. So for example, C6H12O6, all of these elements in this formula can be divided by 6 to reduce them, and we get a simplified, smaller formula, and it's CH2O. Because it can be reduced to that. Now this would have it's an easier formula to write. It has a smaller mass, but we could then change it to a larger formula in the future. But anyway, be able to reduce a formula when given to you. For example, here we have two formulas that contain C's and H's. They have different amounts of C's and H's, but each formula can be divided by a number. Both of them can be divided, and those numbers can be reduced. So these two formulas, even though these are completely different substances, they have the same reduced formula of just simply CH. So empirical means simplest ratio. Can I make it simplified? We need to turn the page. If you didn't turn the page, I forgot to tell you to turn the page. Now you're going to turn the page in your notes, and we're going to look at a problem that is an empirical problem. As far as the ultimate goal is to write a simple formula. And now we have a word problem, and this information was collected from a lab. So this is why you see a lab setup, and this is about the electrolysis of water. What you need to know is you're going to have a word problem, and you need to be able to handle the word problem and know how to answer it. So we read the question. It says a student in a lab experiment decomposes, which means breaks down water into oxygen gas and hydrogen gas, but that's besides the point. And when we do this, we get the following information. We get a certain amount of hydrogen gas, and we get a certain amount of oxygen gas. And this is how we know how to write formulas, because we didn't always know that H2O was a chemical formula from water. But by doing experiments, it led to the development of our chemical formulas. So anyway, how do you solve an empirical word problem? Well, the first thing I need to do is change grams to moles. So step 1, convert grams to moles. Now, why is it grams to moles? Because from the lab, we're able to measure reactions and measure their products, and we can take the mass. And since we have that mass, we can now get to the mole in chemistry. Now we can find some information out about that substance, meaning what atoms make it up and how many atoms of each element make up that compound. So, how does that look? Well, I have two substances that have grams that I need to change to moles. So it's just a simple conversion, very similar to the quiz you took today. You've got to be able to convert grams to moles. So this is what it would look like in the form of a proportion. for hydrogen. So 0.857 grams of hydrogen has how many moles of hydrogen in it? Well, I need the molar mass of hydrogen. Pretty simple. Molar mass of hydrogen is 1 gram per mole. And when I go from grams to moles, I'm going to take them grams divided by the molar mass. And when I do that, I get the same number, which is 0.857. But now it's moles of hydrogen. Now do that for oxygen. Well, I have 6.86 grams of oxygen, and I need to change grams of oxygen to moles of oxygen. The molar mass of oxygen is 16 grams per mole. So I'm dividing that many grams divided by 16, and that gets me the answer of 0.429 moles of oxygen. So I did the first step. I know it's empirical because it tells me what's the empirical formula of water. So that means I have to do these conversions to try to get to my answer being the simplest formula possible for this molecule. Alrighty. So now the next step is, step number 2, is divide by the smallest mole from your conversions, which means these numbers right here. Well, which one's the smallest? Well, it is water. So I'm going to divide everything, all the moles here, I'm going to divide by the smallest mole. So 0.429 divided by 0.429 equals 1. This will ultimately be the number of atoms in my formula. There's 1 oxygen atom in the formula for water. So I'm going to divide the mole amount for hydrogen by the moles of oxygen, 0.429. When I divide 0.857 divided by 0.429, my calculator, I do suggest that we have a calculator in order to actually punch these numbers into my calculator to see if that is true, just to practice this. That's a good idea. We'll just get some time to do that. When you do punch those numbers in the old calculator, we get an answer of 0.199. And you may have more numbers in your calculator, but that tells me some information. Well, empirical formulas are the simplest whole number ratio. Well, guess what, guys? When we do this step here, divide by the smallest mole, we may get numbers that are not exactly whole and have some decimals. But here's the thing. This is an easy number to round to a whole number because it's very, very close to 2. And I'm going to round it to 2, and that's what I call an easy round. When you can easily round a number up to the next whole number or easily round it down to the next lower whole number, then that's good. And so my answer to this question ultimately is a chemical formula. I have math that backs it up, and I have my final answer, simplest whole number ratio from data that was collected in the lab. Turning the page. This one, again, if you don't have a calculator, get you a calculator. Practice the buttons. This is on your unit test. You need to know how to do an empirical formula from data. But sometimes when you do an empirical formula, you get what's going to be a hard round. So when we do this one, this one's a little bit different. We don't have grams, so that's the first step, is convert to grams. This problem here gives me information about nitrogen and oxygen being decomposed, very similar to the water, but we get percents now. Well, percents can be easily changed into grams by doing this. Nitrogen. Nitrogen is 24.5% by mass. So therefore, we just change the percent to grams. Literally, that's all you do is if you see the percent, just know that that's the grams. And now that I have grams of nitrogen, I can convert to moles of nitrogen. The molar mass of 1 mole of nitrogen is 14 grams per mole. And when I do the math, for 24.5, now this is bigger than 14, so my answer is going to be larger than 1. So let's check it out. So 24.5 divided by 14 gives me approximately, you already know the answer because you did it in your calculator just now, didn't you? Yeah. 1.75 moles of nitrogen. Now I need to do the same information for the oxygen. Again, if you see percents and it's asking you for empirical formula is the simplest whole number ratio. You want a simple formula when you're done. So we simply say 70% is now 70 grams. "70 grams of oxygen." 1 mole of oxygen has a molar mass of 16 grams per mole. And we want to know how many moles are in that amount in grams. So I'm going to have a larger than 1 because I got 70 grams, which is several moles. When I do the math, I get 4.375 mole of oxygen. Next step, second step, once I change grams to moles, I look at my moles and I divide by the smallest mole, which that would give me 1. I divide oxygen's moles by the smallest mole, but this time I get an answer that is not easily rounded up to the next whole number or down to the next whole number, because 4.375 divided by 1.75 gets me 2.5. Again, empirical formulas, no formula has decimals. So what do you do when you come up with, when you do step 2, this is a hard round, meaning that you get a mole divided by your smallest mole. One of these numbers ends up being a half. And so what you must do, because our formula is not in 2.5, when you get a half, like in this case here, you will double everything. So there's 1, according to what I calculated here for nitrogen. So 1 times 2 gives me 2 N's. 2.5 times 2 gets me 5. So the empirical formula is N2O5. Should be on the last page. Go to flip. This is just a random compound, actually somewhat interesting. So the smell from cheese is this molecule here. But this is called molecular formulas. Molecular formulas is very similar to the very first slide that we have, as a true molecule. It's what it actually contains, the exact quantity of all the elements in it, and it's the biggest molecule you can have, as far as it is what it is. So anyway, we have in the sentence, we have the word empirical. When you see the word empirical, you always need to know that it is the simplest. We are going to check to see if we have a molecular formula or an empirical formula. So the question tells us that we have an empirical formula of C2H3O. I can't get any simpler than that. That is as simple as it is. I want to know what its molecular. So when I see molecular means true. What its actual formula is. It's going to have possibly a larger mass. So here's how it works. First thing I do is find the mass, molar mass that is, of C2H3O. Add up all the molar masses of those elements. And I get the molar mass of my empirical, the simplest formula you can write for this substance, and that is, let you calculate it real quick, 43 grams per mole. Well, the reason why it's lighter is because it's been simplified. But the actual formula's mass is 80.09. So its molecular formula is larger. This formula has been reduced. And so to know how much it's been reduced by, we've got to do some division. So you're going to take the molecular mass stated in the question, which is 80.069 grams per mole, and you're going to divide it by the empirical mass that you just calculated. And when you divide 86.09 divided by 43, you get in your calculator 2.00, and there's some other numbers, and that's okay. We know that this molecule is actually 2 times as large, so therefore you're going to multiply everything. This is the number. When you do that division there, because those two numbers do not match up, this mass does not match up with that mass, you will say, I need to multiply that empirical formula by 2. So the true molecular formula is C4H6O2. That mass for C4H6O2, if you add it up, will equal 86, which tells me it's correct, because I can simplify this. I can divide everything in here by 2, and that's why the empirical can be written as C2H3O. Now you'll show your notes to the substitute to get your packet to practice all these calculations. You will have a quiz next Tuesday.